Hello, in this video, we're going to be going through lesson 6.1 on properties and attributes of polygons. The essential question is, how do you classify polygons and find measures of interior and exterior angles? Before we can do all of this, we have to talk about a lot of vocabulary related to polygons. So let's start with the definition of a polygon. A polygon is a closed plane figure formed by 3 or more line segments. The shape is closed, which means all the line segments connect at their endpoints. If you look at this picture here, the last polygon that I've shown here, well, it's not a polygon, and because it's not closed. So notice how those two endpoints of the segments do not connect together. The first shape here is a polygon. It meets the criteria. It has 3 or more sides. They are straight line segments, and it all closes up. The middle one here is also not a polygon. Notice how we have this side with a curve. To be a polygon, all of the sides must be line segments. You can't have any curves. Now, the common endpoint in a polygon is called the vertex of the polygon. So you can see in this picture right here, I have a 5-sided polygon with 5 vertices, A, B, C, D, and E. A segment that connects any 2 non-consecutive vertices is called a diagonal. And in the picture, you'll see a diagonal right here. Now, non-consecutive just means not next to. So you want to find 2 vertices that are not next to each other. If I go to B as a vertex and then I connect it to a consecutive vertice like A, notice how that's just making the side of the polygon. A diagonal has to connect non-consecutive vertices so that it looks like the one pictured there. We can also classify polygons as regular or irregular. A regular polygon is both equilateral and equiangular. This just means that all the sides are congruent and all the angles are congruent. So if you look at the pictures that I've provided, the first pentagon there appears to be regular, but I don't want to assume it's regular unless there's markings to indicate that the sides and angles are congruent. So I'm going to add those markings to my example right here. You should add them to your page as well. So I just marked all 5 sides congruent with the tick marks, and I'm also going to mark all 5 angles congruent with this arc mark. So now that I've added those markings, it is a regular polygon. The one next to it is still a polygon. It's still 5 sides, so it's still a pentagon. But it's irregular because all the sides are not congruent and all the angles are not congruent. So if a shape is not a regular polygon, we call it an irregular polygon. So let's highlight the key words that we've discussed so far. We know the definition of a polygon, and we know the common endpoint of the side is called a vertex. We also know that a diagonal connects 2 non-consecutive vertices. The side of the polygon is just one of the line segments. You can see that in the picture. Then we just finished talking about regular versus irregular. The last classification that we have for a polygon is concave or convex. Looking at the 2 pictures here in your notes, one of them is concave and the other is convex. You could probably guess which one is which. The first figure here is concave. See how it's kind of caved in? Now that's kind of informal, but that's what it looks like when it's concave. The formal definition of a concave polygon is that a polygon is concave if any part of a diagonal contains points in the exterior of the polygon. So notice that this diagonal right here, if I draw a point on it, that point is in the exterior of the polygon. The interior of the polygon, I have to be inside the polygon. That point on the diagonal is in the exterior, it's outside the polygon, so that makes it concave. Now, a convex polygon is just the opposite of concave. A polygon is convex if no diagonal contains points in the exterior. A regular polygon will always be convex. So that's going to be really important for us to remember. When we're working with regular polygons, they're always convex. That means if you see a polygon that's concave, it's impossible for it to be a regular polygon. So make sure you have all of those definitions filled in your packet. And now let's go ahead and do one last classification. As I'm sure you're aware, we can name a polygon based on how many sides it has. We can name a polygon based on the number of sides that it has. A polygon with 3 sides is a triangle. 4 sides is a quadrilateral. 5 is pentagon. 6 sides, we have a hexagon. 7 sides is a heptagon. 8 sides is an octagon. 9 sides is a nonagon. 10 sides is a decagon, and 12 sides is a dodecagon. Now, polygons don't stop at 12. It's possible to have a polygon that has more than 12 sides. So if a polygon has n sides, you can name it as an n-gon. And all that means is a polygon with that many sides. So now if it's less than 12, you want to use the specific names that we have here. But if I have a polygon with 20 sides, for example, there's no special name for a 20-sided polygon, so we're just going to call it a 20gon. All right, so now we are going to practice identifying polygons. You might want to refer back to the definition that we just filled out. Tell whether each figure is a polygon, and if it is a polygon, we're going to name it by the number of sides using the names up here. The first figure has all line segments, straight line segments. They connect at the endpoints. And if I count them up, there are 5 sides, n equals 5. That is a polygon. And a 5-sided polygon is called a pentagon. Letter B looks a little bit funny, but let's talk about, is this a polygon or not? Okay, now remember how the polygons have line segments that are straight lines, line segments? Well, I have a problem right here. That's a straight line segment. And here's another straight line segment. So if we use the definition of a polygon, that would mean that the green and the purple are both sides. And technically, I would have 4 sides. I'd have a quadrilateral. That certainly doesn't look like a quadrilateral, and that's because it's not. This is not a polygon. One of the criteria for a polygon is that the segments have to meet at the endpoints. So the line segments cannot cross each other. They cannot intersect. If they cross each other, you don't have a polygon. And then my last one here, it is kind of funny looking, but if we count up the sides or the vertices, notice how all the sides are straight lines. There's no overlap. The line segments meet at endpoints. We have vertices. And if you count up either the sides or vertices, you'll find that you get 8. So this is a polygon, and it is 8 sides, so we'd call it an octagon. The next classification that we're going to practice is telling whether the polygon is regular or irregular. And then we're also going to do concave or convex. Please look carefully at these terms as you answer the question. Now, you're probably looking at these 3 pictures on the screen and thinking, I for sure know that one of those is regular. Part B is a polygon, and it is regular. Here is why. We know it's regular because all the sides are congruent. See how they're all marked with 1 tick mark? We also have all the angles congruent. Each angle is marked with 1 arc mark. So this is a regular polygon, and then it's convex. All the diagonals are inside the triangle. Remember, too, that regular polygons are always convex. So if you know something is a regular polygon, it has to be convex. Now, part A is kind of tempting to say, okay, that's regular, all the sides are the same. But there's a problem here with these angles. See how those angles are marked differently? One has one arc and one has two arcs. Well, they're not the same, or they would have to be marked with the exact same marking. So because these angles are not congruent, that makes this figure an irregular polygon. Now, even though it's irregular, you can still see that this is convex. If we draw the diagonals, and it's a quadrilateral, there's only two diagonals we can draw in, none of the points on those diagonals are outside of my polygon. So it's convex. Now the last picture here is kind of unique looking. It is a polygon, and if you carefully count the sides, you're gonna see that there are 8 sides. So this is an octagon, but the question is it regular or is it irregular? Now you might look at that and say, I think it's regular because the 4 angles are all marked the same. But if it has 8 sides, it should have 8 angles. And there's this extra angle right here that I'm marking in green. And notice how that angle is actually more than 180 degrees. That's definitely not the same as this small angle right here. You can also see that this is concave. If I connect this vertice and this vertice, those non-consecutive vertices, the diagonal is outside of that polygon shape. So this is concave. You can also think of it as it's kind of caved in. Okay, it's concave and it is irregular. Remember that if it's regular, it has to be convex. So just knowing that this figure is concave, which I think is pretty clear by its appearance, any figure, polygon, that is concave will always be irregular. Now that we know how to classify polygons, we're ready to start finding the measures of angles in polygons. To do this, we're going to decompose a convex polygon into triangles and then construct all the diagonals from one vertex. So if I choose this vertex right here, there's only one diagonal. Notice that that one diagonal forms 2 triangles. And if I look at the angles here in these triangles, I'm going to color my corners. So this first triangle, I know that the 3 interior angles in a triangle always add to 180 degrees. Well, the second triangle, if we color those in, well, that triangle also totals 180. So if I have 2 triangles and together those 2 triangles are making that quadrilateral, that 4-sided shape, the total angle sum is just going to be the number of triangles, 2, times 180. So a quadrilateral will always be 360 degrees. And we can do that for other shapes too. Like this next picture, 5 sides has, you can see from one vertice, I get 3 triangles. Each triangle is 180 degrees. So if we calculate 3 times 180, we're going to get 540 degrees. And I could do this all day. You can see that I have a hexagon here, 6 sides. It makes 4 triangles when we look at it. Okay, but hopefully you're starting to see a pattern because math is all about patterns. So if we look at 4 sides, notice that there's 2 triangles. 5 sides is 3 triangles and 6 sides is 4 triangles. So the number of triangles is just 2 less than the number of sides. So in general, if a polygon has n sides, there's going to be n minus 2 triangles, where each triangle is 180 degrees. So that leads us to the polygon sum theorem. The sum of the measures of the interior angles of a convex polygon, so it has to be convex. This doesn't work with concave polygons. In a convex polygon, the total sum of the interior angles is going to be the number of triangles, which is n minus 2, times 180 degrees. If we want to look at just one interior, that has to be, so for the one interior, it has to be a regular polygon, otherwise we can't calculate it. So this side over here is only for regular polygons. So if it's not a regular polygon, you cannot apply this formula. But a regular polygon, all the angles are the same. So if I know that my total is n minus 2 times 180, we can take that total, n minus 2 times 180 degrees, and we can divide it by n, which is the number of sides or the number of angles. And the top, remember, this is just the formula from before. That's my total interior sum. Okay. Exterior angle theorem is a little different. It's actually easier. All polygons, whether they have 3 sides or 103 sides, the sum of the measures of the exterior angles of a convex polygon with n sides is 360 degrees. So it's always 360 degrees for all convex polygons. And that's my exterior angles. Remember, my interior angles are going to change based on the number of sides, but the exteriors will always add to 360 degrees. Which brings us to our final formula. If we go back to regular polygons, if the total exterior is 360 and a regular polygon has all equal exterior angles, just take 360 divided by n, and that's going to be 1 exterior. So these formulas here are really important. Make sure that you've added these to your notes. I'm going to highlight the formulas. And you'll want to look carefully to make sure that you are using the appropriate formula based on, am I asking you to find the interior, the exterior, and then am I asking you for a sum? Or am I asking you for just 1 interior or 1 exterior? All right, so here I have a polygon. Notice the directions tell me that it is a regular polygon. Okay, for this regular polygon, the first thing I need to do is figure out how many sides it has. So if I count up my sides, there's 1, 2, 3, 4, 5 sides. We can name that polygon based on its number of sides. A 5-sided polygon is a pentagon. Now let's calculate 1 exterior angle. The total exterior angle is always 360 degrees. Remember, we just divide by n, where n is the number of sides. So if you take 360 and you divide it by 5, you are going to get 72. So 1 exterior angle is 72 degrees. Now, the exterior angles are going to be angles outside the polygon, and they're formed by extending a side and making like a linear pair. So that's saying that this angle right here is 72 degrees. That is an exterior angle. The next question is going to ask us to find the interior angle. So the interior angle I'm marking in purple. Notice that the interior and the exterior are really just together, forming a straight line. And we know that a line, or a linear pair, always adds to 180. So one way that we could find 1 interior angle is just to take 180 and subtract the exterior angle measure. So 180 minus 72 is 108. So my 1 interior angle would be 108 degrees. Now, there's another way I can get it. Okay, the formula that you have in your notes will also work. In fact, I'm going to need to use it kind of anyways because I have the sum of the interiors. So for the sum of the interiors, that's going to be n minus 2 times 180. Here, n is 5, so let's do 5 minus 2. So 3 times 180. Calculate that, and you get 540 degrees. Well, that's the total sum. So if I want 1 interior angle, I can just take my total interiors of 540 and divide by 5 because there are 5 interior angles just like there are 5 sides. And if you calculate 540 divided by 5, you will also get 108. So 2 different ways to get the same answer. Our last example here is similar to the one we just did. We're given a regular polygon and we want to find the indicated angle measures. The first thing that you would do is you'd count up how many sides there are. And I'd recommend using little tick marks on them so that you don't double count. So there are 15 sides, which makes this a 15-gon. I'd like you to try the rest, finding the exterior angle, the sum, and one interior angle on your own. So please pause your video now, and then when you hit play again, I will have the solution posted. Okay, here are your solutions. And that concludes the first half of this lesson. We'll do the rest of lesson 6.1 in the day 2 video. Thanks for watching. Bye.